Sorry?
You ready?
Yep.
Okay, so the next talk will be given by Roderich Moessner from the Molecular Institute in Dresden, and he'll be talking on topological and flat bands.
I'd like to thank the organizers for putting together this nice meeting. It's a nice combination of good science, good weather, and good food. Speaking of food, I realize I'm the thing that separates you from lunch, so I'll try to be quick, but I'll also probably fail to be quick. And before I launch into this in high speed, I'd like to thank my collaborators. So the two things I really hope to cover today are multi-component Skyrmion lattices and optical flux lattices, which turn out to have a rather unexpected connection, and I'm motivate these things in turn. So I'm going to be really brief on the motivation of all of this, since we've had the school for the last 3 days. Perhaps that wasn't such a bright idea given how many students are left here. But the basic idea is that I think if you've sat through the last few days, then I hope you have not only had an introduction to all of this topological physics, but you probably also believe by now that this is quite an important subject to study. So in a nutshell, there are many interesting settings where new physics occurs. So one of the things to understand is, where does the new physics occur, what kind does it take, and how do we realize this experimentally? And I'll try to say something about the second and third point here. So in particular, what I'll cover is I'm going to talk about multi-component Skyrmions. I'm going to start with an introduction to Skyrmions and flat band ferromagnetism, and then I'm going to give you some new results on what happens in multi-component Skyrmion lattices. And then I'm going to give an example what that means for aluminum arsenide. And then I'm going to probably have to skip the bit on optical flux lattices, on Chern lattices, but then I'm going to describe how the insights on Skyrmion crystals are going to tell us something about how to realize topological band structures in cold atomic systems. Okay, so what's special about flat bands? Well, what is special about flat bands is that the kinetic energy never dominates, and the reason kinetic energy never dominates is because in a flat band the kinetic energy is zero. So, in particular, you don't have a Fermi energy, you don't have a perturbative ground state. This is sort of the archetypal non-Fermi liquid setting. So if you've got a flat band, all these states have the same energy. You start filling electrons into the band. You're absolutely free where to put any electron. The kinetic energy is independent of that. So everything is then determined by interactions, and one of the reasons the fractional quantum Hall effect is such a rich field is because interactions, depending on the setting, can really do a lot of different, lead to a lot of different types of correlated states. So I'll focus on quantum Hall systems near integer filling. I'm going to go into that in some detail, and in particular, I'm going to give an introduction to the physics of Skyrmions, which Jim Eisenstein very, very briefly alluded to yesterday, and then take it from there. So this I'm going to be extremely brief on, because that is something that Joel in some part covered. So electrons in 2 dimensions moving in a strong magnetic field simply have cyclotron motion at a cyclotron frequency which is proportional to the magnetic field. If you've got a motion which has a fixed frequency independent of its amplitude, that reminds you of a harmonic oscillator, and in fact the energy levels are those of a harmonic oscillator, and then n, the excitation index of the harmonic oscillator, is known as the Landau level index. And the important thing is that each Landau level is degenerate, because basically you can center the cyclotron orbit wherever you like. And this degeneracy turns out to be given exactly by the number of flux quanta threading the system. So each Landau level is this flat band, which is n phi, the number of flux quanta, times degenerate. And the ratio of the number of electrons to the number of flux quanta is what we call the filling fraction. And of course, in graphene, which you have and will hear much about in this location here, the spacing between the Landau levels is different. The wave functions are different in detail, but the degeneracy of the Landau levels is exactly the same. So much of what I'm going to say actually applies there as well. So what's flat band ferromagnetism? Well, flat band ferromagnetism is what you learn electrons should do before you find out that most materials actually are not ferromagnets, but antiferromagnets. So basically, flat band ferromagnetism can be really easily understood. So imagine you have 2 electrons which only feel a mutual Coulomb repulsion. Then by the Pauli principle, they need to be in an antisymmetric wave function. Now, if you want to minimize the probability of two electrons being in the same place, you want to put the spatial wave function into an antisymmetric combination, because that vanishes at r equals 0. That means you need a symmetric wave function for the spins, and a symmetric wave function for the spins is a symmetric wave function, and therefore a ferromagnetic alignment of the spins. So if you now take a Landau level, which really has two copies, one for spin up and one for spin down, and you fill it so that there's one electron per flux quantum, so that half of these two Landau levels is filled, then you don't need any Zeeman energy. You actually get an interaction-induced gap, because all the spins by this argument would like to align, and then you have a ferromagnet, and then there's a gap to flipping one spin, which is basically purely an interaction effect. So in other words, at nu equals 1, you have a state which manages to be a topological state, because it's a quantum Hall state, so you've got edge states and so on, but it also has conventional order because it's a ferromagnet. It turns out these two things are going to interplay in a rather intricate fashion to give you the physics of Skyrmions when you start taking individual electrons out of the filled Landau level. Okay, but this is really the important first thing. At nu equals 1, there's a ferromagnetic state, and then we're going to ask what happens, what kind of excitations does this ferromagnetic state have? Well, you know, ferromagnets have spin wave excitations, which is something we're not going to treat in any detail in the first part of this talk, even though I come back to them later. But the important thing is they also have Skyrmion excitations, which turn out to have a net charge. So let me briefly explain to you what Skyrmions look like and why we call them topological objects. So basically, you can think of Skyrmions in the following way. So first I need to introduce to you the stereographic projection, which you've probably come across before. So imagine you have a sphere, and you can map a sphere onto the infinite plane by a stereographic projection by drawing a line from the North Pole to a point in the plane, and then you identify the point on the surface of the sphere where the line pierces the sphere with that point in the plane. So that the point at infinity, that the North Pole gets mapped on basically the region at infinity, the South Pole is the origin, and all the other points get mapped on different points in the sphere. Now you get a Skyrmion by the following prescription. Define a vector field which points normal to the surface of the sphere everywhere, and then you assign the direction of the point of the spin at the point where the line of the stereographic projection crosses the sphere with a point in the plane where this line hits the plane. So then at the South Pole, at the origin, the spin points down. At the North Pole, at infinity, the spin points up. And in between, the spin twists from pointing down to pointing up. And if you look at the in-plane component, it essentially looks like an XY vortex. And if you look at the out-of-plane component, you simply get a twist from the spin pointing down at infinity to up at 0. So that's what a Skyrmion does. And you see that the Skyrmion, in that sense, is a mapping from the sphere to the sphere. You basically have a vector field defined on the surface of a sphere, which you then map by the stereographic projection onto real space. And this mapping turns out to have non-trivial topological classification. So in particular, a spin wave, according to this classification, is topologically trivial, while the Skyrmion, which I've shown here, is topologically non-trivial and has a winding number z equal to 1. And as I'll explain next, this winding actually comes along with a quantized charge at the same time. So what I've described here now are the excitation properties of a ferromagnet, and these are going to be connected to the topological properties of the quantum Hall effect in what follows. So I'm not going to give you an introduction to Barry phase and flux, because I cannot possibly do in one slide what Joel did much, much better in his introduction to all of this. So let me just skip to this rather busy slide on how Skyrmions actually work. So imagine you've got so the first thing, if you remember what Joel said about Chern-Simons theory, so fundamentally, the quantum Hall effect is a commensurability effect between flux and charge. So whenever that ratio, the filling fraction, is a simple rational, 1 to 3, or 1/3, 1/5, 2/7, and so on, then you get these incompressible states with these topological properties. So if you remove an electron, you screw up this commensurability. And somehow you'd like to get back to it. Now, which knobs can you turn? So you can't, of course, you can put back in the electron, but that's cheating, because the entire point was that you took it out and you wanted to have an excitation in there. You could adjust the strength of the field, but imagine that this is fixed. Are there any other options you have? And it turns out there is another option you have, and this is that the ferromagnet can actually generate its own internal gauge field, and it generates its own internal gauge field by putting a twist into the spin state of the ferromagnet. A twisted spin state comes along with a Berry phase, and it turns out that a skyrmion, which has this topological charge equal to 1, exactly gives you a Berry flux, which is also equal to 1. So by putting in a skyrmion, you generate an internal flux, which, when added to the external flux, perfectly reestablishes the commensurability between flux and charge. And that's basically why skyrmions are topologically stable, and why the topological excitation of the quantum Hall ferromagnet conspires with the sort of topological properties of the commensurability of the quantum Hall physics to give you these skyrmions as low-lying excitations. Okay, so basically the idea is if the electrons follow the local spin texture adiabatically, then they see a Berry phase. This Berry phase exactly gives rise to the Berry flux that reestablishes the charge flux commensuration.
So how many electrons can I remove before this breaks down?
This is a question of detailed energetics, which I cannot. So this really depends on a lot of things. So, to some degree, it's like asking how many quasi-particles can I put in the Landau level until I get to whatever the 2/3, 4/5 state and so on. This is in part a statement about the relative stability given a particular disorder realization of fractional quantum Hall states. Okay, there are another really few cute features about skyrmions, which is there's an entire class of skyrmions, namely those which are parameterized by a location-dependent spinner, provided the spinner components are analytic functions. The spin stiffness energy for all of these families of skyrmions are exactly the same. So you can basically rescale the skyrmion in many different ways. You always end up with something which costs exactly the same energy. You basically see that this is scale invariant because there's a gradient squared here, and there's a two-dimensional integral, so basically the units of length just cancel out perfectly. So you can parameterize these skyrmions, it turns out, essentially by completely if they by analytic functions, and if you only specify the location of the zeros of the analytic functions, you've fully specified the skyrmion. So for instance, up to a scale factor. So for instance, the skyrmion I just showed you is parameterized by a spinner which looks like this, where z is the complex coordinate in the plane x plus iy. Then the actual skyrmion real experiment size is set by a competition. The Coulomb energy would like the skyrmion to be as large as possible so that the charge is spread out, whereas the Zeeman energy would like it to be as small as possible so that the number of spins flipped is minimal. Okay, by the way, did I mention that somewhere? Failed to mention one of the lecturers here in a previous incarnation worked on skyrmions and actually wrote a rather nice review on this topic. Okay, so I'd like to talk about multi-component skyrmions. So multi-component, I've just explained everything with spin, but it turns out it's much more general than that. All I needed to say is that there was an internal degree of freedom. So you could not only have a spin degree of freedom, you could also have a bilayer degree of freedom like Jim Eisenstein talked about yesterday, so that there's a pseudo-spin whether you sit in the bottom or on the top layer. In graphene, you consider the K or the K prime point. It turns out that the spin and the and this sort of valley index in graphene together give you, to a first approximation, an SU4 invariant problem. And then you could look at bilayer graphene, and so it goes on and on and on. So you get potentially a high symmetric state plus a set of generic anisotropies, because there actually is a distinction to whether you twist a spin or whether you move from one layer to the other. And so you can study each of these problems separately. But what's useful is to have a unified starting point where you can basically have an analytical theory for each of these to start putting in the specific features. Okay, so here's this detailed theory. And I'll obviously have to skip over a lot of details, but I'd like to give you the basic flavor of what we've done. So for a two-component skyrmion, for a two-component system, so spin up or spin down, you need a two-component spinner. For a d-component system, so d equals 4 in graphene, you need a d-component spinner. And so an SUD spinner is also known as a CP-d-1 spinner, because for a spinner you can basically set one entry simply to 1, because the overall phase and the overall magnetization and the overall amplitude do not matter for spinners. Okay, now a single skyrmion, as I said before, the spin twist energy is minimized provided these psi's are all analytic functions. And the number of zeros of these analytic functions tells you what the topological charge of the skyrmion is. So charge 1 skyrmion has 1 zero in each of these, charge 2 skyrmion has 2 zeros, and so on. So, and that's basically, and so there's an exact result which states that no matter where you put these zeros, you get exactly the same spin energy. Now, if we don't take out one electron, but a finite density of electrons, then we don't need one skyrmion, but a finite density of skyrmions. And in particular, these skyrmions can then form a lattice the same way that electrons in the Wigner crystal form a lattice. So I'll now discuss the case of a skyrmion lattice, which we conveniently think about having d charges per unit cell, where d is also the size of the spinner. And then it turns out the minimal spin twist energy is still given by holomorphic functions. But as you know, there is no such thing as a periodic holomorphic functions, but the next best thing is a theta function, which is almost periodic. It's almost periodic in a sense that the spinner doesn't care about. And now the important insight here is that if you want to span this holomorphic space, you can do this with only d basis functions. So there are d linearly independent theta functions, and between these you can span all of these possible skyrmion lattices with d charges per unit cell. So there's a particular way that we parameterize these. So you've got lattice translation vectors, and the angle phi here basically tells you which angle the lattice vectors make. So phi equals pi over 3 would give you a triangular lattice, and phi equals pi over 2 would give you a square lattice. And now the important feature is the general skyrmion lattice is now simply parameterized by one matrix, which has order d squared entries. So whereas you are specifying a skyrmion texture across, which is a continuous function across the entire unit cell, you actually only need order d squared coefficients to do this. So these are, before you put in any interactions and anisotropy, no matter how you choose this U, they are completely degenerate, so any skyrmion crystal has the same energy as any other one. And then it's only when you lift the degeneracy by interactions and anisotropies, which we'll do next, that you then get a selection of a particular skyrmion crystal. So the real progress in doing this is that the space that you need to search has really become very small. From starting from continuous functions in 2 dimensions for each of these d components, all we need to do is now search a space of these matrices. And what is this controlled in? It turns in that this treatment is controlled in the spin stiffness. As long as the spin stiffness is your largest energy scale, then there's basically a gap to the all excited to all the other parameterizations which we've basically thrown out. Okay, so to cut a long story short, we thought about this for a long time, but one useful picture that we did, that at least I found useful, that we came up with in the course of all of this is these theta functions have zeros. I told you to parameterize skyrmions. Zeros is a very natural object to think about, and it turns out you get a very high density of charge provided there's a zero of each type, of each flavor of skyrmion near the point where you're looking. Now, you can basically understand this. You get charge because the spinner twists. This is the Sperry phase physics. Provided there are zeros of each flavor nearby, that means that each spinner component goes to 0 relatively quickly, so the overall direction of the spinner changes fast. Whereas if one zero is very far away, that means that component is large, and then no matter how much the other small components change, the direction of the spinner is going to remain very similar. Okay, so if you want a uniform charge density Q, what you basically would like to do is spread out these zeros of the different components so that at any given point, the closest set of all zeros is as far away as possible. And so this is one way that we found of doing this. So you basically make rows of these zeros, and this is what we call zindon crystals from some high energy piece of work. And apparently zindon, which is the zero, is a Persian word for castle or something. I don't know how people came up with this. Okay, but then, so basically all we have, this U matrix I showed you before, is a simple diagonal identity matrix now. And then we can basically ask, what is the, is this actually minimum? And we can, say, optimize this angle here, but we've actually done a very extensive search for these states. So I should just briefly say, of course, we weren't the first ones to study these. So I've shown here the D equals 4 crystal. So bilayer gallium arsenide, there's been a lot of work on, particularly the question when you have internal degrees of freedom, which are spin and layer by Moon and friends, and then dynamics and anisotropy. There's been a lot of work in time-dependent Hartree Fock by Cotier, and I'm going to show basically analytical versions of much of that. Okay, so having done all of this, it turns out the crystal I just showed you, the zindon crystal, actually is a the ground state of the skyrmion, of the multi-component skyrmion for general D. And the way we've checked this essentially by explicit energy minimization by different search algorithms over the space of matrices, and then we've also checked for local stability by the excitation spectrum. So this has got a number of interesting features. So one is that it fully breaks the SUD symmetry. So it's like an antiferromagnet, which basically, like a magnet which isn't collinearly ordered, which isn't coplanarly ordered, but really which is ordered in which uses all the different directions for its order that is available to it. And the other thing is that the charge periodicity is actually much smaller than that of other observables. So the spin periodicity here, if you look at this, stare at it for a while, you see that you have to go over several unit cells of the charge periodicity, and the charge periodicity basically for SU2 over several unit cells looks exactly like the same for SU4. So in other words, you have a highly charged periodic crystal like a Wigner crystal, but the individual observables like spin and so on are highly entangled with each other, and they have a larger periodicity. Okay, and the Coulomb interaction therefore doesn't distinguish between these. It's going to be other anisotropies which do that. Now it turns out that if you have a Skyrm lattice, you can never have a uniform Coulomb energy, which would obviously be the way of uniform charge density, which would obviously be a way of minimizing the Coulomb energy. Rather, you always have a mean charge plus some modulation. As I said, the modulation has a small periodicity, which we'll see later simplifies the equations of motion, but there's a particular simplifying feature. If D becomes large, the modulation A becomes exponentially small, and B is basically only a simple harmonic. So this modulation Q of R is an exponentially small quantity times just a cosine, and then the higher harmonic is just a cosine squared with another exponentially small number. So if D becomes large, you can simply create one of these zindon-Wigner crystals, which is essentially just a simple sinusoidal modulation of the charge density. Okay. And numerically, what you find, even if you only have 4 components, like in graphene, the actual charge density variation is only a lot less than 10%. So things become very uniform. Whereas if you have a 2-component skyrmion crystal, the charge density variation between the minimum and the maximum is 100%. So this convergence really is rather fast. Okay. Now we can also look at the dynamics and excitations of these crystals. And I'd like to tell you in several steps what happens. So without interactions in anisotropy, as I mentioned, the holomorphic space is fully degenerate. So we can choose these parameters anyway, and the energy is degenerate. That means all excitations energy are strictly pinned to 0. And then the other excitations have a gap, which is the size of the spin stiffness. This is what controls our treatment. If you then add a Coulomb interaction, this has the rather unpleasant feature that the charge density already is quite a nonlinear function of the spinors. And then the equations of motion you get are really nonlinear. So it becomes very messy mathematically. But the cute thing is, if you analyze this in symmetry in as much detail as you can, what you need in the end of the day are only 2x2 matrices for each wave vector with entries which are very complicated form factors, but they're just geometric properties of the theta functions, and the properties of your zindon crystal is independent of these. So you once have to work out these theta functions, and then on top of this, these theta functions form factors, and on top of this, all you have to do is solve 2x2 matrices. And for this reason, we can do these calculations in the thermodynamic limit, which wasn't possible before, and we can also do it rather fast. So you see these continuous curves with a lot of resolution. That's basically new to this treatment, and it's also new for two-dimensional skyrmion, two-component skyrmion crystals. Okay, so what does the excitation spectrum look like? Well, the first thing that you notice is that all the d-squared modes that were there, so I said if there were no interactions and anisotropies, everyone would be degenerate. Now, if you add in Coulomb interactions, all the d-squared modes actually remain gapless. So it's not like some get gapped and others remain gapless. Every single one, the maximum number of gapless modes that you could have had do remain gapless. And if you do the counting in a bit more detail, the SUD Lie algebra has d-squared minus 1 generators, and then there's one essentially translational magnetophonon mode, which is very well known in other contexts. There are some further features like roton minima at finite, or so-called roton minima at finite wave vectors, which again, one finds live in several bands and so on.
Does disorder gap all of the gapless modes, you think, or do some of them remain gapless?
Yeah, so I think this is exactly the same as Wigner crystals and so on. So the Magnetophonon mode is a thing which is charged, so that's the same as in the Wigner crystal. The other ones are spin wave modes. But although the spin wave modes are globally neutral, but if they are not collinear, then they still have local charge densities. So I'm not entirely sure what happens there.
But Zeeman gap will be there, right, for spins.
I haven't done anything about anisotropies. I'll come to that next in like 1 or 2 slides. So there's a huge low energy density of states because of all these low energy modes. So what that tells you in particular that you expect a rather low melting temperature. So actually observing a Skyrmion crystal for high D is going to be even harder than for low D. And then where all of this started was looking at NMR, resistively detected NMR experiments on gallium arsenide bilayers. We've taken a detour which took us like 2 years. There should be very fast NMR relaxation again because there's this huge low energy density of states, but we're only just starting to calculate this. Okay, as I said, the Magnetophonon mode one can easily identify because it actually depends on the details of the interaction. If you have Coulomb interactions, you get a different power law than if you have delta function interactions, and you get yet a different power law if you've got logarithmic 2-dimensional Coulomb interactions. So you can easily identify the Magnetophonon mode just by looking at that. And in our treatment, this is again very simple. All you need to do is change V of k, and then everything else falls out. Okay, so Bastwan just asked about anisotropy. We decided to look at SU3 anisotropies for a number of reasons. So A, no one's done that yet. B, SU3 anisotropies are different from the bilayer case, which people have looked at so far, because bilayers, you always, or in these graphene type problems, you always have this very natural product structure for D larger than 2, that you've got spin times layer or spin times valley. Whereas here, SU3, you really have three equivalent internal degrees of freedom. So one place where this appears, for instance, is an aluminium arsenide, where you have 3 different valleys. And if you grow your sample in the 1, 1, 1 direction, then you basically get this projection of the different pockets of charge carriers, which are anisotropic. So you've got an anisotropic effective mass tensor, but the 3 are rotated by 120-degree rotations. So this anisotropic effective mass tensor, so you have a CP2 spinner with 3 entries corresponding to the 3 valleys. Then there's an anisotropy, which simply comes from the fact that there's an anisotropy in the effective mass. And that's something you can calculate. It's got the following form. It basically wants the spinner to, like a Zeeman field, which wants the spinner to point in a particular way. This is more like a nematic anisotropy, but it again favors a pure state where where it's only one valley is occupied rather than one which is mixed. Okay, now what happens when we increase the anisotropy to the spectrum of excitations? So here I've just shown the low energy excitations. There are 9 of them. There's the Magnetophonon, and then there are 8 others. From the 8 others, 2 remain gapless, and then there are 3 different gaps. And I've plotted the gap as a function of anisotropy strength here. So some of the gaps open linearly, other ones open like a square root. And again, all of this is something we can analytically calculate relatively straightforwardly. The other thing that happens is that the crystal becomes a square crystal. So with 0 anisotropy, you start with the angle that the zindon crystal makes at 120 degrees. At very high anisotropy, you end up with a square lattice. So this is always a charge density. And in between, you get a continuous crossover between the two. And for aluminium arsenide, there's some recent theory paper by Grayson where we've taken out the parameters that we need. And just the estimates are that the anisotropy energy is of order of 5 Kelvin. Spin stiffness energy is roughly 10 times larger. And then we estimated if you are sitting like 10% away from nu equals 1, you're sitting in a limit where you've got a square Skyrmion crystal rather than a triangular one. So this is rather satisfying that after doing all this theory, you can actually make pretty detailed predictions what should be happening in a particular material by putting all the numbers in, which one gets from, say, K.P type treatments. How much time do I have left?
We have 10 minutes.
Okay, so let me come to the second third of my talk. 10 minutes. Okay, let me just be brief on that, and, because that's important for lead over into the third bit. So the fractional quantum Hall effect, so this concludes the bit on Skyrmion lattices. I'm now going to say a few words about fractional quantum Hall effect on lattices. Then I'm going to tell you how we can use what we've just learned about Skyrmion lattices to realize the kind of lattices that exist here in optical and with optical means. So pioneering work by Haldane has basically showed that you can get the quantum Hall effect even in lattices which have zero net flux. And the way this essentially happens is that you go to a lattice where the bands in reciprocal space, and this is again something that Joel has covered, have a non-zero Chern number, so that there's basically a net flux the same way that there's a net flux in the Landau level. And then when you go to fractional filling, you get states which are morally equivalent to fractional quantum Hall states. So and these are known as fractional Chern insulators. The two questions I'd like to the two questions which are important, one of which I'm going to address here, is the role of flux uniformity. It turns out you can't actually have uniform flux throughout the Brouillard zone, and this has some consequences for the stability of these states. And then the other question is, how complete is this analogy to fractional quantum Hall physics? Can you see different fractions? Can you see hierarchies and so on? And also, can you see competing states? And these are the two questions I'm going to address here. Okay. So, right, so the first thing, Joel mentioned the pseudopotential for two particles in the Landau level, and one of the questions we asked is there a simple analogy that you can make also for the lattice-based systems. So just to remind you, Haldane pseudopotential basically is a parametrization of an interaction after you've projected it onto a Landau level. And so for fermions, spin-polarized fermions, you only have odd pseudopotentials. And what changes as you go to a lattice is that you no longer have the center of mass degree of freedom neatly separate out from the relative degree of freedom, so that instead of having one number, one pseudopotential, you now get different pseudopotentials as a function of center of mass degree of freedom. But even though there's no longer a single number, we nonetheless found that this gives you a useful heuristic. So if you simply take next nearest neighbor electrostatic repulsion between electrons, project it onto a flat Chern band where the quantum Hall effect is particularly stable, you see that you've got a large first Haldane pseudopotential V1, then you've got a smaller second pseudopotential V3, and depending on the range of the Hamiltonian, you actually get an entire further sequence of these Haldane pseudopotentials. So just from this, you'd expect the nu equals a third state to be strongest, the nu equals a fifth state to be present as well, but much weaker, and so on. So the papers which founded the field a couple of years ago were by the Chamon, Wen, and Dasama, our Chandrasekharan lecture here, groups, who had basically pointed out that there does exist this primary fractional quantum Hall set at nu equals a third, and therefore got the entire field running. For the checkerboard lattice, which I showed here earlier, we found that there's also nu equals a fifth state, and this for instance, you can find by threading. So if you do numerical simulations, look at the spectrum on a torus. If you thread a flux, what you find is that after you thread it in 5 flux quanta, so this is the flux threading thought experiment that Joel also talked about, you basically get the 5 different topologically degenerate level exchange their places, and then you get back to where you started from. And this tells you that you've got a nu equals a fifth state, and then you see a gap between the topologically degenerate levels to all the other levels up here. What we also found were hierarchy states. So we found a very good evidence for nu equals 2/5. In fact, this plot here is for nu equals 2/5. But then with decreasing confidence, we found 3/7, 4/9, 5/9, and so on. So one of the things you notice here is that all of these are less than or just a little bit larger than a half, and none of these are actually sort of close to filling fraction 1. And this is because there's in fact absence of particle Hall symmetry in these Chern bands. So there's particle Hall symmetry when the filling fraction goes to 2 minus nu, but there's no particle Hall symmetry when the filling fraction goes to 1 minus nu, the same way that in the spin polarized and quantum Hall system with spin, there's no nu going to 1 minus nu strict particle Hall symmetry. And it turns out actually what you find is that there's an effective one-hole potential. So there's even a one-body term, which isn't present in the Landau level for reasons of translational invariance, when you make the particle Hall transformation nu going to 1 minus nu. And this one-hole potential is actually not particularly small. So just to show you how the quantum Hall states destabilize as you go make the filling fraction larger and larger, this effective one-hole potential becomes more and more important because you have to start filling in really high energy states there. So whereas at nu=1/3, if you basically plot as on the x-axis the one-hole potential and the y-axis the occupation of a particular state corresponding to this momentum k, you find that nu=1/3, the occupancy is pretty close to 1/3. Sorry, this is nu=1/5. At nu=1/5, the occupancy is pretty close to 1/5. At 1/3, it remains rather close to 1/3. But then as you go to higher and higher fillings, like here at 3/5, it becomes more and more unequal. So you're basically forcing modulations on the charge density onto a fractional quantum Hall effect, which a fractional quantum Hall effect itself really doesn't want to have. And so then this gets steeper and steeper, and if you just take the maximum slope of n of k as a function of filling fraction, you see that this maximum slope starts off near 0 and then just seems to more or less diverge at some critical filling fraction. So you basically see that it's this effective one-hole potential which actually screws up the quantum Hall state when you come close to nu=1. Okay, so my final thing that I like to do is pull these two threads together and tell you what we can do in order to generate more stable optical, more stable Chern bands using the insights I've just derived for Skyrmion crystals. Two fields which don't have very much to do with each other a priori. And the reason I noticed that they had something to do with each other is because I listened to a talk by Nigel Cooper, who was doing a construction which at least looked a lot like a zindon crystal. And I told him, I don't know what you're doing, but this is what you want to do to get a better version. And then we sat down together and figured out what I'm going to tell you about now. Okay, so basically what we'd like to have is a Chern band which is as like a Landau level as possible, so that the flux density is as uniform as possible and that the kinetic energy is as flat as possible. The way we do this is the following. So you consider now, and this is motivated really by cold atomic physics, you consider an atom with n internal states. So this is what we call D for the electrons earlier on with mass m and momentum operator p, which is subject to a periodic potential V. Now, the starting point of all of this is that if you do optical lattices, they're very naturally formulated in k-space, because if you absorb a photon and you change an atom from level A to level A prime, and you absorb a photon at wave vector k minus k prime at the same time, it's really like taking the atom in reciprocal space and moving it to a different location in reciprocal space. So what you then basically end up with is, if you think about this directly in reciprocal space, and you just forget about the kinetic energy for pedagogical reasons initially, then what you simply have is a hopping problem in reciprocal space. Okay, so basically you go to reciprocal space, you have a hopping problem, you get a Bloch theorem for reciprocal space. So this is all basically the other way around than what you're normally used to. And then you want to solve for coefficients C of wave functions of the atom at a particular momentum and at flavor alpha. And the hopping matrix is simply given by your by your laser potentials that you're putting in. So the important thing here is there's an inversion of the role of direct and reciprocal space. So what's the conserved momentum in the Brillouin zone normally becomes a real space position, and what's flux in real space becomes the Chern number in reciprocal space. So what we need to do is generate a Chern lattice in reciprocal space to give us a flux distribution in real space. Okay, so root to uniform flux, you take multi-component atoms, and what I've just told you about the exponential accuracy of uniform flux, a flux uniformity for the zindon crystal makes this more precise, but it's connected to like the Hofstadter problem in weak fields, where the Landau levels basically emerge as being almost perfectly flat if you've got a very small number of flux per plaquette, and therefore many plaquettes per unit cell. So the idea is now basically to realize the mathematical structure of the zindon crystal by in reciprocal space using a hopping problem where you've got flavors 1, 2, and 3, which can then, by absorbing and emitting photons, move between the different flavors and different points in reciprocal space. So this is a little bit too much to digest in real time. But what you basically find if you Fourier transform this back is you get, in a different representation, precisely the flux density distribution of the zindon crystal I showed you earlier, which is now a real space flux density distribution. So basically, if you take 4 copies of these, this is exactly the same picture I showed you for the D=4 zindon crystal. So in particular, the bands are very flat. So if you look at for some parameters we've put in, this is the density of states as a function of energy. The flat band here has a width which is basically imperceptible on the total bandwidth of the problem, and a peak which is very, very high. And the Berry curvature is also very uniform. This is exponentially accurate uniform Berry curvature I mentioned earlier. So for d equals 4, the flux density meanders around the mean by only plus minus 10% in either direction. So basically, by taking a relatively simple hopping problem where you have very simple regular phases, e to the I pi over n between different components in reciprocal space, you immediately get an artificial artificial magnetic field in real space, which is very flat and very accurately, which is in a band which is very flat. And there are currently attempts to actually implement this with rubidium-87 atoms, which are three component, which have 3 internal degrees of freedom. Okay, so let me then summarize. So I've tried to tell you that topological and flat bands are interesting. So I've told you how to think about Skyrmion lattices, how to parameterize them, how to compute the properties of the excitations, what is the Skyrmion lattice which is optimized by the Coulomb interaction, and then what the excitation spectrum looks like in the absence and the presence of anisotropies. I've said a few words about fractional Chern insulators and the stability of fractional quantum Hall physics there. And then I finally concluded by saying, so this is actually in part prompted by a question that Zahid asked, do you actually have an experimental version of any of these flat bands? So the answer, the honest answer is no, but I think it may be one of the cases where optical means actually may do things which are really, really difficult just using materials physics. So I'd like to...
That anything we propose, if it is impossible to do in condensed matter, cold atom people can do it. I do not see much more a reason to be optimistic, because even if they make it, what are they going to look for? I mean, in cold atoms, they can make various things, apparently. But then they look at all of them by the same technique, and, some of the beautiful things we have, like quantized levels, they're gone. So do you have some idea about how to look for it? Smoking gun looking, not some
I can answer this on several levels, and of course, religious wars can be fought out over many centuries, as we know. But okay, so first of all, on the humility front, you tell me how you diagnose a spin liquid, and then and then we can come back to the cold atom experimentals. No, but it's just. Right.
The whole point of spin liquid is nothing happens, and people are excited, right?
Okay. Right. So then the reason why, so then you raise two issues. A is, are they actually better at us than at realizing these things? And the second question is, even if they manage to do it, what will be the game?
One is my concern.
Okay, so the second one, because I had an answer to the first one. Okay. so the first one, the answer is basically, there are certain things like, relative hoppings, nearest neighbor distance, and so on, which are really hard to fine-tune using materials, because they, you pull on one side and everything else moves. With a design strategy like this, which is really natural for cold atoms, which is not natural for condensed matter physics, there's a structure which you can realize very naturally just by, this tight binding in reciprocal space. Which then, okay, good, right. And the second one, I have to say to some degree that is a challenge to us rather than necessarily to them. So you can certainly look at thermodynamic quantities like compressibility and so on. You can look at noise correlations, but there's a lot of work there to be done. I think the problem, so coming back to the religious slant of things, the problem is perhaps that in the cold atom community, not enough people challenge themselves to do that. But perhaps some of the young people will be motivated to.
I have 50 papers on cold atoms proposing various quantum phases. I'm not making it up.
Right. The papers or the quantum phases?
But it's like one of those promising assistant professors, very brilliant, always promising. And I'm serious, and this is 7 years, 10-year time,
Okay, so even though I think where the cold atom community has gone new ways, like in non-equilibrium dynamics, they've done things which most of us would not have imagined earlier. So I think a search strategy where you ask a priori, what are we better at doing than the others, is the rational search strategy, and what you shouldn't be doing is looking through PRLs and asking, what is there on the menu.
Is a good subject for cold atom to look at. But I was asking, what about this new one?
Well, I think, some more hard work is needed, okay.
Quick,
a naive question. I mean, do you think measuring entropy through thermal measurements or something of that sort would be a better way to probe the presence of the flat bands, or spin liquid behavior?
So there's always a distinction between necessary and sufficient. So what you need to convince one of your friends and what you need to convince one of your enemies. So the general problem looking at dynamic quantities and going back to microscopics is that this is really not, this is really a one-to-many mapping. So if you have entropy together with a number of other things, like transport and so on, then you can say, okay, all of this gives a picture which is coherent. But you basically say, here I've got a really totally cool new topological state of matter, and I can prove it because the entropy is blood, and people are going to say, okay, I mean, please do a little bit better. But I certainly agree that doing characterization of easily measured quantities is the first step, but it's definitely not sufficient for featureless phases that we're looking for.
I actually had a quick question. It was sort of the first version of Shankar's question is that how complex is it to get the zindon crystal using lattices?
Okay.
Like basically, how many lasers do you have to phase lock, etc.?
You need two things. You need an appropriate atom, and then you need the appropriate matrix elements. Mm-hmm. So if a d equals 3, it's still very natural because basically, because you basically only ever have triangles in this lattice, and so this is why 87 rubidium is being tried, because you're going from 1 to 2, 2 to 3, and 3 to 1 is symmetric. Mm-hmm. If you now have a bigger matrix, because the zindon crystal itself isn't permutation symmetric, fully permutation symmetric, then it becomes more complicated. So the first thing that's actually being tried is to do an 87 rubidium 3 components zindon crystal, and then take it from there.
Well, the part I was thinking about is in terms of lasers. You're putting this atoms in some kind of optical potential, right?
I'm not a cold atoms person, and how actually to do this, that is gets really messy, but it's, and I can't tell you any of the details because I don't know them, but it's something that, Jean Dalibard is actually trying to do rather than just thinking about. So it's not the kind of, here, please take 10 components and take 200 lasers, so it's not that.
Oh, it's not, okay. Right. So I guess if there are no more questions, let's thank Roderich one more time.
I'm not allowed to accept presents.